don't know how to do it, but now we'll see. Oh gosh, I'm so nervous.
That's forward, that's backward,
Okay.
and that's your right.
Okay, thank you.
Okay.
I can actually go there.
Okay, last speaker this afternoon is Ruriko Yoshida from Kentucky. He's going to talk to us about partitioning the sample space on 5 taxa with a neighbour joining algorithm.
First, I would like to thank for all organizers for giving me here and giving me great opportunity to give a talk today. So the title is not really fitting what I'm going to talk about, but this is a basically teaser for the possible talk in December. I'll be back in December, so hopefully I can advertise actually my talk in December. Okay, so so we start off. This is not end of this talk. This is a starter for this talk. Usually, I end usually like at a future work, but this is my first page. Okay, so earlier talk, he actually explained that the minimal evolution method, really detailed, and also neighbor joining method is a greedy algorithm to find the ME tree. And ME method has a time complexity NP hard. This is NP hard problem. And the neighbor joining method, its time complexity is polynomial time. So this is polynomial time algorithm. So it is very nice. So question is, we want to, from this point of view, the neighbor joining method is optimal when the algorithm outputs the ME tree. So we want to ask how often neighbor joining algorithm returns the ME tree. That means the output from the ME and the output tree from the neighbor joining method have the same tree topology. So this is joint work with called Eichmeyer, Peter Huggins, and Leo Pachter. So it's coming soon, hopefully. So the neighbor joining, so like earlier talk, we know that neighbor joining tree for large data set loses so much information, and we don't know exactly how well it performs with the pairwise distance matrices, which are estimated from using MLE. So our goals are analyze the behavior of the neighbor joining method on 5, 6 taxa and more. Actually, you can, this is generalized, so you can do this more, but actually for 5, 6 taxa, I can actually explain to you more combinatorics way. And also, we want to show that the neighbor joining tree topology is determined by polyhedral subdivision of the space of dissimilarity maps. Actually, also the ME tree topology is also determined by polyhedral subdivision of the space of dissimilarity map. So basically, what we do is comparing those two subdivisions. Okay, so here's the notations. I mean, it's kind of confusing. Sometimes I'm talking about the pairs. Sometimes I'm talking about the leaves. So here are the leaves, and here are the pairs. Okay. All right. So neighbor joining algorithm. That is, so before that, we call a pair of leaves a cherry if there exists exactly one intermediate node on a unique path between them. And here's actually like distance matrix of tree. And this is a theorem by Saito-Nei and Studia Kepler, and it is also called the Q criterion. So Q is the n by n matrix such that defined by QAB equal to DAB minus RA plus RB over n minus 2, where RA is the sum of DAK, K is from 1 to n. So the theorem says that A star B star is a cherry in T if this Q A star B star is a minimum for all AB. Okay, so quick outline of the algorithm is So input is the tree matrix and output is the additive tree. And then we initialize a star-like tree, and then we find the cherry using this Q criteria and compute the branch length from the interior node to each leaf and repeat this process until we find all cherries. Okay. So we looked at Q criterion really closely. So the resulting matrix, again, this is symmetric, and we can see it as a vector. So we vectorize instead of like matrix, but we can vectorize, and the dimension m that n choose 2, just like the input data. And then actually Q criterion is actually linear transformation Q equal an times d, where d is a vector representation of the distance matrix d, and q is a vector representation of q, and the entry of matrix an is given by this guy. Okay. So for example, like n equal 4, a4 equal this guy. Okay. So the Q criterion is basically we want to find the smallest Qi, I equal 1 through m equal to n choose 2, and such that Q equal n times d. Okay, so before doing like details, here's actually nice lemma. So this is called shifting lemma. So this is due to Mihaly and Dunleavy and Leo-Pachter. And there is an n-dimensional linear subspace of Rm, which does not affect the outcome of neighbor joining method. So this can be written as specifically this vector. And this means that basically a tree where a leaf A has distance 1 from all other leaves, but otherwise all zeros. Otherwise, so this is also called the shifting vectors. So we know that actually the partitionings are actually like has some linearity of this. Okay, so the first step in cherry picking, after computing Q criterion Q, the neighbor joining method proceeds by finding the minimum entry of A, or you can say maximum entry of minus Q. And then, therefore, the all parameter vectors D for which neighbor joining method will select cherry I. In the first step is the normal cone at the vertex minus IE. IE is just regular unit vector, and of the polytope of Pn, this guy, convex of this guy. And by the shifting lemma, this is not full dimensional, so the dimension of the affine dimension of this polytope is actually m at most m minus n. Okay, is it clear? Okay. So now we are trying to reducing the number of taxa, and so without loss of generality, we assume that just n minus 1, and n just we pick the cherry, and then we put the new node that is n minus 1. And actually, so this is an explicitly formula for this guy, and the reduced pair pairwise distance matrix is 1 row and 1 columns less. Okay, so this one also we can see as linear transformations, and d dash equal r times d, such that r is this expression. And this proceeds that cherry is repeated until there are only 3 taxa left. Okay. So this can be for all n. So this is nice. So basically, what's going on is the first time we pick a cherry, and this is actually nice, actually cone, but we are actually adding the more inequalities of the cones. So this is, for example, n equal 4. This is simple. So this is the subdivision. So this is actually 3 dimension because okay, so the actually affine that's 6 minus actually 2 dimensions. Sorry, 6 minus 4 equal to 2. So this is 2 dimensions. So, okay. All right, so for n equal to 5, we can actually, so, actually, there is only one unlabeled tree. So that I can actually permute that actually all taxa number using S5. And then actually without loss of generality, so here is the actually inequality, explicit inequality. So that's a first picking cherry. And then we are adding more inequalities. Okay? So I can actually say the 4, 5, and 3. That means that 4, 5 I actually pick. That's actually, we have the taxa 1, 2, 3, 4, 5, and I pick the 4, 5, and then I pick the 1, 2. So 3 is the left in, lonely node. So he means actually pair, but he's just lonely. Anyway, so that is actually, so this is actually inequalities, and just you can permute just like taxa number. Okay, so even n equal to 5, this is actually, so I said that that's actually, so we have, how we pick, we have different cones. So even though we have same actually tree topology, like 1, 2, 4, 5, that is like cherry, and 3 is lonely node. We have 2 cones because how you pick the cherry, we have the 2 cones, and those cones, those cones do not form really nice. Do not form a fan means actually they don't intersecting really nice. And also the union of the cone, 1, 2, 3, that means that I pick the 1, 2 first, and 4, 5 later. And also for the cone, 4, 5, I pick the first, 1, 2, I pick the second. So they have the actually, so all distance matrices of these cones return the same tree topologies, but they don't actually, I take the union of them, they do not form a convex body. So we have actually example, specific example in the paper, I don't remember, but so it's not nice. They are not nice, actually, cones, union cones. Okay. So n equal to 6 gets more complicated because there are 2 unlabeled trees, and also actually one way to pick, actually even this case, actually I think this case, we have 2 ways to actually do group actions. So there are 3 different group actions, and okay, so here are the more details of this. So that this is actually type 1, that's how, so basically this is in a figure 1A. Okay, sorry, so this one is actually for 2 types, sorry. So this one is 2 types, and just this one is just 1 type. And we have 1 type, that is actually how we actually pick the node, and that gives the actually this group actions. And so there are 19 cones, and for one tree topology we have 6 cones, and this one we have 180 cones, and there are 2 cones for one tree topology, and 180 of them, and there are 2 cones. Actually, 2 cones plus 2 cones, 4 cones for actually one particular tree topology. So it's getting more complicated to represent actually all neighbor joining cone in terms of combinatorics. Actually, this one I'm going to skip. I have some simulations, but I'm going to skip. So here's actually future work. So this is actually, so title is on the optimality of the neighbor joining algorithm by called H. Meyer, Peter Huggins, Leo Pachter, and myself. And in fact, also ME tree topology is determined by polyhedral subdivision of the space of this similarity map, like I represented. And by comparing those 2 polyhedral subdivisions, we can study the optimality of the neighbor joining algorithm. And so actually, we have some teaser, like I said, this is a teaser of the next talk. So we investigated especially subdivisions for n equals 10, less than 10, because it's so hard to compute. I mean, it's because, of course, ME method, it is NP hard. So computing the actually polytope. Actually, this subdivision is very nice. This is actually the union of the all ME cones. Those form a normal form. That means that there is a polytope. There is a nice polytope representation, and actually ME algorithm can be seen as a linear programming. So it's very nice. However, actually the vertices of the polytope has actually exponentially many. So it's very hard. But so n equal 4, actually it is 100%. So that's exactly overlapping. And n equal 5, it is 99.5. So notice that there is only one tree topology for unlabeled tree topology, so 99.5. And n equal 6, we have two different. So for the caterpillar, we have 91.34, and cherry, the 3 cherries, that's another one, we have 90.34, and for n equal 7, it's about 78.87 for 2 cherries, and 3 cherries, 82.746. So you notice that it's dramatically decreasing. Actually, I know that n equal 8, but I just didn't have time, space, so I didn't write down, but it's about 70% overall. So hopefully it will be submitted somewhere soon. And thank you so much for your attention.
Okay, any questions?
Quick question: How do you compute those percentages?
Huh?
In the last slide, how do you compute those?
Okay, this is great question actually. So because we have a cone, right? So how are you going to compute the percentage? So actually, what we did was we intersected with unit square, and then just we computed the volume, compare the volume of the intersection that is the spherical polytope. And that's actually, so we computed the volume of spherical polytopes, and then just we calculated. So it is not, that's why I say it is not, it's about, right? So basically, we didn't know exactly how to calculate the volume, spherical, like volume of the spherical polytopes. So we approximated using the Hessian, I think that is basically metropolitan Hessian algorithm, I think. Yeah, so that's what we did. So this is what it's about. But yeah, so.
Okay, that brings us to the end of this afternoon's session. Just remains for me to thank all of this afternoon's speakers once more.